Okay, so thanks very much for having me, and I apologize, I got off a plane about 2 hours ago, so I'm still trying to adjust. But I'm taking a little bit of a different tack here. I work mainly on the agricultural model intercomparison project, which I'm happy to talk about later on in some of the sessions. But today I'd really like to talk a bit about the prospect of using global climate models to evaluate and understand our agricultural management decisions. Yes, perfect, thank you. Our agricultural management decisions. Now, in the project that I work on, AgMIP, it's called for short, the focus has primarily been in understanding how climate change impacts food security by way of impacting crop yields and crop production. And that is a necessary, exceedingly important, important thing to understand. I like this figure because it shows, it's simple, but I don't have a really good way, sorry if I'm pointing at anybody. It shows really that, our agricultural systems are embedded within greater environmental systems. And when we modify the surface for agricultural management, we're changing the surface characteristics and the way our agricultural systems interact with all the climate system components that we see. And so from a climate modeling perspective, what we're interested in is how do the surface characteristics change when you move from natural vegetation to agricultural systems, and then when you utilize intensive management on top of that. Now, there are multiple things that we care about, and I'll just discuss quite a few here. The first is albedo. We're really concerned about the reflectivity, right, of our crops and the change between natural and agricultural systems. We're interested in water content, the water retention of the soil, the water added for irrigation, the water content in the above ground biomass. These are other things that could change the way agriculture interacts with the environment. We're also interested in surface roughness. If we supplant a forest with an agricultural field, that's going to change the local circulation systems, perhaps even the microclimates of these regions, and that's something we have to be concerned about. And the last thing, sort of as a catch-all, we're interested in the interactions between the land surface and the overlying atmosphere, the exchanges of heat and moisture and energy that result when you go from natural to agricultural systems. And now, as you can see, this is a map of cropped areas, and it's arguable that India presents a really compelling and dramatic example of how an agriculture, a landscape dominated by agriculture can impact with a very dramatic and extreme climate system that you have here. Now, I should say the utility for doing this is that if we can understand not just the impact of climate change on agriculture, but also of agriculture on the environment, it helps us to better plan and build that into our decision-making processes. Now, I'm going to argue that amongst all different management techniques we could be looking at, irrigation is perhaps a dominant forcing that should be considered amongst climate model simulations, and that's something we've been looking at for a while. This is a map of irrigated areas, and I don't need to tell most of you, as most of you know, aside from, let's say, eastern China, India represents the most intensively irrigated places on Earth. Now, again, I don't have to tell you this, but in terms of the region, the most heavily irrigated areas are those in northern India and the northwest region, and Rajasthan and Punjab and Haryana. And then as you move towards the eastern part of the Indo-Gangetic Basin, towards the west, the withdrawals are exceeding recharge rates, in some cases quite significantly. This also happens to be a pretty important region for the establishment of the early monsoon circulation, which I'll talk about in just a minute. So what we've been trying to do in some of our recent studies using the GISS climate model, which is the model that I work with at our institute, is to take this global map of irrigation and put it into the land surface component of our climate model and try to understand what the global and regional effects are. What you're looking at here is the partitioning of surface energy, of sensible heating on the bottom and latent heating on the top. And you're looking at the difference, the latent heating and the sensible heating due to irrigation, once we include irrigation in our simulations. And I'm sorry, my color bars dropped off, but the sensible heating here, the blue indicates a decrease, and the green indicates a substantial increase in latent heating. Now, with latent heating, really what we're talking about is evaporation, and that can result in a substantial evaporative cooling. And when we look at the surface temperatures, that's something that becomes quite apparent. Particularly, what we've broken it down here is by season. It's dry, it enables more, and as you evaporate more from the land surface, the evaporative cooling effect becomes more prominent. And this lasts mostly in the dry season, all the way up through March, April, May, which happens to be, again, a very important season for the buildup of the monsoonal circulation. Now, in addition to the really intensively irrigated areas in an important region for the monsoon, the other thing that we have to consider in our model simulations is the impact of the increasing irrigation trend, okay, which is sort of from the advent of the Green Revolution, and as we've built up the irrigation infrastructure and capability to extract water, our irrigation rates have increased. That's both during the monsoon season, then you'll see dry season down here. And this has enabled India to become a very major global contributor to our global grain stores, and has been really advantageous. But we have to consider this trend alongside the increasing greenhouse gas trend that we see as well. And so the question that we're really trying to ask with these simulations is, what does the impact of all of the surface water that we've added by way of irrigation, this one management strategy, what effect does this have on the monsoon circulation? Now, I don't have to tell you, there are many components to the convergence zone as the northern hemisphere heats up that has to be considered. There are temporal and spatial distributions of rainfall that have to be considered. There are other modes of climate variability, El Nino, the warming of the Indian Ocean, that also have to be considered. For the purposes of this talk, I'd like to focus on this overturning circulation that we see here. Due to the buildup of the temperature gradient between the northern Indian land surface and the equatorial Indian Ocean. It's this early onset phenomenon, this early monsoon season circulation pattern that I'm interested. And I'm interested in this primarily for is hard to come by, and so in lieu of data, we have reanalysis data sets that we use. Now, in addition to uncertainty amongst the different climate models, I just should point out that there's uncertainty based upon what data sets you use as well too. You can see the top data set, the NCEP 20th century reanalysis, looks quite different from the other two. In part, that's because of the way it assimilates the data that's used to drive this model. The ERA 40 and the NCEP CDC are very closely correlated, and although there are differences between those, if I were going to validate my model for the monsoon circulation strength, those are the two I would probably use. Now, we can kind of tease out some of the major components to the monsoon circulation that we're interested in. And one of the driving components of the strength of the monsoon is really the temperature contrast between the northern Indian continent, which is really heavily irrigated, and the equatorial Indian Ocean. So what you're looking at on the plot are 4 simulations that we ran. The temperature contrast, the difference between the continent and the ocean, is on the y-axis, and you see the time series here. The gray and the green series indicate our control simulations, so those that did not have irrigation. The orange and the blue show our simulations that did incorporate irrigation, and in both cases, there's a significant declining trend as we increase irrigation. Our temperature contrast is decreasing as we increase the irrigation rates. And a weakened temperature contrast is going to lead, it correlates very strongly, it's very strongly related to the intensity of the monsoon system. Now, we can look at this a slightly different way and look at that lower level temperature contrast again against irrigation. So the more we increase irrigation, again, the more we weaken our temperature contrast. And I should mention in both plots, the blue indicates our irrigated simulations that also have the increasing greenhouse gas trend. So when we include greenhouse gases, that contrast decreases further, and that's also partly because of the warming of the Indian Ocean that we include in those simulations. Okay. The other thing that we're interested in looking at is the impact not just on the monsoon strength, but the variability in the monsoon strength from year to year. And so that's what you're looking at here. It's a 10-year moving coefficient of variation of monsoon intensity. Again, the green and the gray series that you see up top here are our control simulations, no irrigation, and you can see the interannual variability varies quite a bit. The group of time series you see down here, the blue and the orange again indicate our runs, our model simulations that incorporated irrigation, and the other three are the reanalysis data products. So what we take from this is that in order to better, not fully, but better simulate the monsoon's observed interannual variability, we need to incorporate irrigation. Without irrigation, our model is unable to reproduce the monsoon, and that has effects for our model projections when you use them in your water resource and agricultural assessments. Okay. So we're interested in monsoon strength, but overall what we're really interested in when we talk about the monsoons are the rainfall. In terms of monsoon circulation, what I'll speak to here is the moisture, the water vapor transport. And under both irrigated conditions, so irrigation only and irrigation including the greenhouse gas, our water vapor transport decreases, and it's actually quite significant when we include the greenhouse gas forcing. Now, these are just our model simulations. What we'd like to do is actually compare them to what others have done, and believe it or not, there's been quite a few studies on this topic, specifically for India in the last few years. On the left, you'll see a study by Ellen Douglas that looks at not the transport, but just the amount of water vapor that's in the atmosphere. And you can see that it increases quite a bit under irrigated conditions, I should say, over the most intensively irrigated areas, which is something that we would expect. The issue, though, is that it's not well distributed over the continent, and it does make for some interesting and major differences in water vapor distribution for the continent, which has an impact on the in situ precipitation that we care about. On the right is a study done by another climate model also looking at the impact of irrigation, and you're looking at April, May, June, July moisture transport. And the red indicates declines in moisture transport. And this particular study found something very similar to what we did, is that in the early season, May and June, okay, the moisture transport declines quite heavily in June. So sort of this onset period that we care about. One last way to look at this, what you're seeing here is from that same paper, the surface temperatures and rainfall differences that result, again, when you include irrigation in our climate model experiments. And what you see is that in May, irrigation results in a cooling, as we expected, towards, again, the early part of the monsoon season, really when this temperature is ramping up on the Indian continent, on the northern Indian continent. There's a cooling, and then there's rainfall declines. That actually indicates a decline across most of May. So this is latitude, and this is sort of averaged for the entire Indian continent is what you're looking at here. Now, the bold lines that you see here is the monsoon onset over Kerala, the sort of standard metric that's used under control simulations when you do not include irrigation. Once irrigation is included, we see when you average all of these simulations together that the monsoon onset over Kerala actually is delayed by about a week, if not more. So again, another reason to really consider all of the forcings, the regional forcings, and that's not just man-made climate change, that's also our agricultural decision-making, our management decisions on our regional climates. And we have to think about how our irrigated areas and the intensified irrigation in our irrigated areas affect our dryland farmers if the water transport is being impacted. So, significant amounts of irrigation regulates the surface temperatures, which we expected. This results in a decrease in the temperature contrast that drives the monsoon circulation in the early part of the season. And that really acts to temper the amount of water vapor that's being transported over the continent. And so we argue, amongst all of these studies, and not just ours, that irrigation is a significant, if not global, regional forcing that needs to be included in our climate model projections for India, and currently is not part of the suite of projections for the IPCC. And when we include irrigation, we can actually start to better represent the monsoon processes here that are very important for your region. And I think I have just a couple more minutes. I just want to quickly touch upon and make a point. So I work primarily with the Agricultural Model Intercomparison Project, and what we're trying to do is take all the climate models we have available, all of the crop models who are willing to join us and available, and some agroeconomic models, and understand the impact of climate change on food security. And water resources is a key interaction that we're looking at. I just want to make the comment that this has been largely a one-way set of studies, and that the climate group passes on our information to the crop group, who then passes on their information to the economists. And that's, again, a very necessary exercise. What I hope that you glean from this is that once you make your decisions, your management decisions, particularly regarding adaptation, that those need to go back into the climate models, and there needs to be interaction with the climate modeling community to understand how different management decisions impact the regional environment. And so far, that's not a connection that's been undertaken regionally around the world very much, and that's something we're hoping to foster. Just quickly, 2 more slides. I just want to make a quick plug for our water resources project. Clearly, there's room in between the climate modeling and the crop modeling for a big water resources intercomparison. And what we'd like to do is take the precipitation projections. Right now it's domestically in the US, domestically focused, but take the precipitation projections and use our information about how rainfall will change and how it's distributed in crop water resource modeling and water balance modeling. The idea is that if we can understand how our reservoirs will change due to changes in rainfall, we can then better model how this water is partitioned to different uses. And ultimately what we're looking to do, and I'm not expecting you to, again, to read that, but what we're looking to do is say, to our crop modelers, okay, let's pretend now that you have, or not pretend, let's project that you have a very limited amount of water and not an infinite irrigation well for your crop model. How does your crop respond under these conditions? And that's the step that we'd like to move towards. And we'd like to do this not just for the US. Right now we actually have a project in Central Valley, California that's been funded and that we're working on. We'd really like to take this model, this framework, and apply it in India, in China, and in a lot of other heavily irrigated areas that could use the information. And so last slide, right now we're domestically focused for our water resources initiative, but we are seeking global collaborations. And if you're running a water resource model, particularly if it's set up on a district level or sort of a watershed level around here, we'd love to talk about how to integrate our framework and use our framework in India and other places. So we're hoping for global collaborators. We're also in the stages of planning our next AgMIP water workshop. And so if you're interested in perhaps hosting that here, we'd be happy to talk with you about that. And Jonathan Winter, I should plug for him really fast, is running this initiative. And so you can feel free to email myself or him for more information on the project. And that's it. So thank you very much for having me speak.